In this lecture, we're going to review how to write a force in Cartesian vector form if the force is given directed along a line. So here is the overall idea. If a force is directed along a line, like shown on this figure to the left, then we can represent the force vector in Cartesian coordinates by using a unit vector and the force's magnitude. Keep in mind, a vector has two components, a magnitude and a direction. So the unit vector represents the direction of a vector, and the magnitude is the magnitude. So in the given example here, we can review the steps. The first step is we can locate 2 points on the line of action of this force, A and B. And from those 2 points, we can find the position vector RAB. Along those AB points can be any 2 points on the line of action of this force F. The next step, we can find the unit vector describing the line's direction. Unit vector U hat. So if you're going to write on paper, since this is printed, so it doesn't have the hat on top of it. But if you're going to write the unit vector on your engineering paper, then you want to write U hat. Subscript is AB. So this direction is along the AB direction. The unit vector equals to the position vector RAB, which is defined by the 2 points on the line of action, divided by the magnitude of RAB. So there's another way to write the magnitude of a vector is to use the absolute sign. And now we have the direction, so the last component or last step would be to multiply the unit vector by the magnitude of the force to have the force represented in Cartesian vector form. Let's see one example. 2 forces are acting on the flagpole as shown in the figure. FB has a magnitude of 560 Newton and FC has a magnitude of 700 Newton. So the magnitudes of both vectors are given. And now we're looking for the magnitude and the coordinate direction angles of the resultant force. So think about how can we find the magnitude and coordinate direction? So magnitude and direction, those are the 2 components of a vector, right? So when you're looking for the magnitude and coordinates direction angles, or the direction of a force, that means you want to write the force in Cartesian vector form. So in this form of I, J, K hat term, and from there, we can find the magnitude and the direction of a vector. And to find the resultant vector, we just need to find FB and FC in vector form, then we add them together. So the overall plan can be find the forces along the AB and AC in the Cartesian vector form, because when they add them together, the resultant force will be shown in Cartesian vector form directly as well. And then we add them together. From there, we can determine the magnitude and the coordinate angles of FR. So the first step is to find a position vector along FB and one position vector along FC. Right? So let's take a look at FB force first. So on the line of action of FB, we can find 2 points. Well, actually there are unlimited choices of points, but only 2 points are available, or we can only find coordinates of 2 points. One is point A and one is point B. So we can find one position vector RAB. And to find the position vector RAB, we need to find the coordinates of B and then subtract the coordinates of A. We can do one thing. Let's write down the coordinates of B here, and B, the x coordinate for B will be 2, right? 2, and then for y coordinate is -3. So 2, -3, and 0. So this is one way to put the coordinates of point with a pair of parentheses and put the coordinates inside it and separate by comma. So x coordinate, y coordinate, and z coordinate. And same idea for A. Since A is on the z-axis, so we have 0, 0, and 6. And let's find C as well, since we're going to look for our AC later for the force FC, right? So we will need the point C as well. So write down C point here. So we have 3, 2, and 0. All right. So RAB will be the coordinate of B, subtract the coordinate of A. Okay, so we do the subtraction. B subtract A. 2 minus 0 is 2, -3, and 0 minus 6 is -6, right? And same idea, RAC will be C minus A. Okay, so the direction is important. Do not use the coordinates of A minus coordinate of C. So coordinate of C minus A, so you have 3, 2, -6 as the position vector coefficients or components respectively. And since we're looking for the unit vector along each direction, so we also need to find the magnitude. So this is the position vectors and their magnitude. So magnitudes, just square root of sum of the squares. All right, from there we can find the unit vector of each position vector by using the position vector divided by the magnitude of the position vectors. So this is for FAB. FAB equals to, or let's write down the formula first. Force vector equals to the magnitude of the vector times the unit vector. Okay, so for FAB, it has the same direction as RAB. So we're going to use the position vector RAB divided by the magnitude of RAB to get the unit vector of RAB, which is also the direction of FAB, and times the magnitude, which is given 560. And we do the math, and we find the vector, Cartesian vector form of the force FAB. And same steps for FAC. The magnitude of FAC is 700, which is given, and it has the same direction as the position vector RAC. So position vector divided by the magnitude of it, you will have the unit vector UAC, which is the direction of RAC, also the direction of the force FAC. Magnitude times the direction, which will give you the force vector FAC. Okay, with both forces written in components format, we can add corresponding components together to have the resultant force expressed in Cartesian format or component format, IJK format. The reason we do this is because we need to find the magnitude of the vector and also the direction cosines of this vector. So the magnitude will be the square root of the sum of the squares. And direction cosines will be the ratio, or we are looking for direction angles, right? Direction cosines will be FA magnitude of x component divided by the magnitude of the force. This is cosine alpha. So we use the inverse cosine alpha to get the angle alpha. And beta will be the inverse cosine of the y component over the magnitude of the force. Same thing for gamma angle, which is the angle between the vector and x, y, z axis respectively. Now when we look back for at our solutions, here is something you need to keep in mind. Usually when you have a problem look like this, where you have the magnitudes are given and you have points given, it's an indication that you're going to use this format. A vector equals to the magnitude of the vector times the direction of the vector, which is a unit vector. So since the magnitude is given, right, the only information you need to look for will be the unit vector. So the unit vector will be directed from the points on the line of actions. So the unit vector will equal to one position vector defined by the 2 points divided by the magnitude of the position vector. And you plug back this unit vector to the formula you've chosen. You can write the vector in Cartesian vector form.